So it's a great pleasure to have today Massimiliano Gubinelli from the University of Bonn. And as you see, he will speak about the infinitesimal generator of the stochastic Burger's equation. So thank you very much, Massimiliano, to accept.
No, thank you to you for this invitation. I am really glad to speak in Rio. I'm less glad not to be here there actually. Yeah, and this is a topic which I think fits very much somehow, because I started to work on this topic with Milton, and once in a while I have to read into your books to find things about the particle system and learn. So I'm not an expert at all. So if please intervene, make questions, and also ask things so that I can ask you also other things. So let me give you the plan. So this is experimental way. Let's see if it works. Okay, if it does not work, then we go back to standard way. Okay, so this is the motivation. We want to study the martingale problem of certain singular SPDs. In particular, I will use as an example the Burger's equation. And let me give you a brief outline. Yeah, you see, I start to have problem. I don't see my cursor. Okay. So yeah, so our main the things I will tell you apply to some models, which are somehow models which were difficult to deal with and remain open for some time. In particular, I will use one model all along the talk, is Burger's equation in one dimension. So this is the derivative of the KPZ equation I will introduce later on. And then somehow this is a prototype for singular SPDs. Okay, it's an SPD which somehow is a partial differential equation or is a dynamical system, as you can look at it in many different ways, but essentially it's a dynamical system where the vector field is quite irregular. Okay, so it's not clear how one should define somehow the infinitesimal evolution of the system, okay? Because on the natural state space, the drift is not well defined. Yes, and I will introduce a martingale problem for this. So this is a probabilistic technique. Okay, I will speak mostly about a probabilistic approach to this kind of singular SPDs, since either solution of KPZ and other things, there are other ways to solve these SPDs, but I'm concentrating in the martingale problem. Okay, so we have the martingale problem, and then I will discuss a bit the existence, and then how you deal with uniqueness, and this will be done as usual somehow in this kind of things in the martingale problem by looking at a PDE, which will be infinite dimensional in this case. And then this introduces the main subject of the talk, that is, okay, we have to deal about, we have to understand the PDEs associated to an operator, which is the generator in the equation. And then the problem is, what is a proper domain? And this introduces somehow, yes, the main topic of the talk, this idea to have, so the domain we will see is not a classical domain in some sense. I mean an explicit domain for this operator. Okay, it's not something you see every day, and this was the main idea of our works. And more or less I will talk about, okay, all the material I will talk about comes from a paper I wrote with Nicholas Perkowski maybe 2 or 3 years ago already, and this is called the infinitesimal generator of Burger's equation. It appears in PTRF this last year. And also somehow I together with a student, PhD student, Mattia Turra, we wrote application to a different kind of equation, but somehow at the same time we rethought a bit what we were doing, because I told you, so somehow it was really new material for us, especially also for me. All the functional analysis involved was quite new, and And you, from the initial paper to this paper, you see some evolution in our arguments. I don't still fully understand the picture, so I would like some input maybe from you, that people like Claudio know maybe many things much better than we do, or I do at least. And then even more recently, just to tell you that the picture is still was not very clear, there is a, I think, nice contribution of a master student with Nicholas, Lucas Grefner, which I saw it's in the audience, which has wrote somehow simplified some of the arguments by using some more standard theorem. Okay, I will tell you exactly where. And this is still a master thesis. Maybe I think that there will be a paper coming out. I hope so. Anyway. But I will not speak in detail of the argument, because I am reading it and I'm trying to make to connect with what I understood. Okay, so I will speak mostly of this work with Perkowski and the technique we use there, essentially. Okay, so that's the plan. So let's go on. Let's go on. I need to move on. Let's see. Yes, good. Okay, so first thing first, so let's give you what is the object of our consideration. So the stochastic Burger's equation, and I can formulate very easily. So okay, at least informally, I can formulate very easily. So the goal is to construct. Okay, to study the wellposedness for this equation. Okay, so this is an equation for a one-dimensional function which depends on space and time. Space could be either a torus or the full space, depending of how you feel more natural for you. I think analytically it's maybe thinking about it, it's easier on the torus, but the technique really don't care at some point. So you can think both situation, maybe particle system like more to think of the full space. And this is the equation, okay? So this can be introduced in many ways, like fluctuations of some hydrodynamic fluctuation of some model, but somehow for me, I'm a PDE guy, so this is for me is a PDE. The difficulty in this PDE, this is a Laplacian, so you have like diffusion, then you have this term, which is like, it's written in this way, but essentially is a transport term. U is a velocity and U is transported with U, and you can integrate by parts because you are in one dimension and just write the derivative of U square. But think about it more as U gradient U. So this is a transport term. And U, we name U because essentially we want to think about it as a velocity field. And then you have the gradient of the space-time white noise. Okay, so the equation is the gradient of a current. So it's a conservative model. And you want to have here a space-time white noise because you think somehow that this is some scaling limit of a microscopic model where the noise enter like microscopically with the microscopic correlation. Okay, so at the macroscopic level, the correlation are essentially at range 0. And the idea, so of course now everything it's for, okay, you could define this equation rigorously, but the problem, every time you can understand rigorously, this is a Laplacian, this is like gradient U squared. The problem is that when you put all them together, in particular with the fact that somehow you expect that the invariant measure for this equation, for example, let's say on the torus with 0 mean, because I told you it's conservative model, so you conserve the integral of U, it's conserved, so let's choose it to be 0. And then the Gaussian measure, which is given by white noise on the torus, let's fix on the torus for the moment, okay? So white noise on the torus with 0 mean is expected to be the right invariant measure, an invariant measure for this system, okay, for this equation. So that's, and now you start to see a bit what are the problem, at least at the intuitive level with this equation, because if you expect the white noise to be an invariant measure, actually ergodic also, then you expect somehow that the solution looks like white noise at any given time. Okay, so that's the idea. So what I mean by white noise, I mean that U at a given time, essentially, if it's started stationary, you expect that U at any given time as correlation is Gaussian and as this correlation, okay, given by delta function. In particular, U at a given time, you cannot expect to be a function. Okay? It will be a distribution of negative regularity. So in one dimension, this essentially means that U has a regularity, you can say U has regularity. So you have to imagine that, for example, U has the regularity of the derivative of a Brownian motion. Okay, somehow C minus 1/2, meaning where order space are meant negative order space, you are meaning this is the derivative of a order 1/2 function. Okay, let's say, let me define as the derivative of some order 1/2 function. Okay, so this is the kind of regularity you expect from the space white noise. Okay. So if you use distributed like mu, then it has this regularity. Okay, I put circa here because we have this technical point that we want to restrict the mean of the Gaussian process to be 0. So this is strictly not true, but there is this covariance minus at m, which is nice, which I don't want to write because I don't remember what it is exactly, but it's not important. And I told you this, so now you start to see the problem, I hope, in the sense that, well, if U has this regularity at any given time, it's not clear what is U square, and essentially, of course, all the other terms can be handled somehow in a weak formulation. Okay, you can test with a smooth function and then put the derivatives on the smooth functions here and there. But of course, this term you don't have very much to do. You have to have a way to handle the square of the white noise. Okay, and this was the problem associated to this equation and to the KPZ equation in general. So the relation with the KP, I don't write KPZ because we will never need, but essentially you should think about the equation satisfied by the primitive, a primitive of U, and essentially it's the same kind of equation where here you have, instead of derivative of U square, you have derivative, you have the square of the derivative of H. Okay, and then you have additive white noise based on white noise. And this equation was open for a long time. There were initial contribution of Bertini and Giacomin, which somehow found a way to take the limit of a particle system to converge to the KPZ equation, but the correct formulation of the equation was not clear until Eirer came about, essentially around 2013, and also Milton and Goncalves. They formulated various notions of solution. Maybe it's even, this is even before, I don't remember exactly. They formulated two different notions of solution for this equation, and somehow we are following in this talk somehow the approach of Jarre and Goncalves of energy solutions. Okay, I will explain it later. Good, that's the problem. Okay, so let's move on. I will be more precise in which sense I want to solve this equation. And we want to solve this equation in the sense of a martingale problem. And okay, this is somehow classical. I think there are people here which know everything better than me, especially how to write Varadan. Okay. And the idea is I want to describe this process as a stochastic process as a stochastic process, okay? Because there are plenty of strategy, especially I'm going back just, all these strategies from Eirer and then regularity structure of paracontrol distribution, they took a pathwise point of view. They really look at this equation as a PDE and try to solve it as a PDE. While the method, somehow the martingale problem formulation really think to it as a process, stochastic process, and then what you do is that, okay, you compute this process on given test functions, which maybe can depend on time, and then you prescribe that these these real valued processes now, they satisfy, okay, they evolve as a martingale modulo a correction term, okay? And this correction term somehow describe the deterministic part of the dynamics, and the martingale describe the innovation contributed by the noise term, okay? And okay, this martingale, you have to prescribe the quadratic variation. I would not insist on it right now. Actually, you can read it from the generator as soon as I tell you what is the generator. And so the generator at this level, it's just what you have to put there. It's just a linear operator which tells you a recipe what to put here in such a way that you can correct to get a martingale. Okay, that's how I understand the martingale problem. Okay, so it's not really, so somehow it's a very concrete operator. Okay, if you arrive from this point of view, you think of this generator a very concrete operator which is defined on very smooth functions, because you will need to apply it to formula somehow. And that's somehow the setting where you want to fit, okay? The problem of, and this is still formal, okay? Because part of our work will be to get the right setting where I can formulate a martingale problem, okay? I'm not sure if there are questions. Claudio, do you want to interrupt me, or I take all the questions at the end? Okay.
No question. Can go on.
Okay. Please interrupt me if there are some questions. Okay, there is no problem. Okay, so this is still heuristic, but of course you already seen some martingale problems, so you can guess what should be the generator, especially if you take, for example, we will take Galerkin approximation that somehow the generator looks like this. Okay, looks a linear part which somehow takes care. So I go back. We will have a linear part which takes care of the linear equation, which is Ernst-Uhlenbeck, and then you have an additional drift term which takes care of this drift. Okay, so the linear part, essentially this is the drift given by the Laplacian, and this is the contribution given by the noise via Ito formula, and then you have the nonlinear drift. Okay, and I give them two different names, so L0 and G. So this has to be taught as a differential operator in infinitely many variables. Okay, the idea is that you can differentiate. This is something like this. This function. So the U is a function. So the U is the state of the system at a given time. So it's a function on the torus with mean 0. And then phi is any functional of this function. So we will use cylindrical functional, for example, and then you have to take derivatives because somehow you think of it as like an infinite dimensional second order operator. And the drift is an infinite dimensional first order operator. And these derivatives are like Malyavin derivatives, but I will be precise here. I don't want actually to be too precise, just somehow want to give you a feeling, but if you feel puzzled by some notation, please let me know. Okay. In my mind, this is like an infinite dimensional second order operator. Okay. This is how I want to think about this operator. Okay. This is a Laplacian, then you have a first order part, but actually they go together because somehow you are working not on a flat space, but in a space where you have a Gaussian measure. So this is the right operator to consider, the right equivalent of a Laplacian in this context. And then you have a first order operator which encode the drift, okay, the nonlinear part of the dynamics, and therefore a drift. Okay, and this will cause all the problem for us. So let me be more precise still about this martingale problem, and somehow give more details. Again, okay, I would not be extremely precise because, I mean, things get much complicated afterwards, and maybe it's better to concentrate on the ideas more than on the details. The first thing is that, okay, what were this function phi of u, where you want to so how you want to characterize your process? Okay, the idea is that, okay, my process is a process evolving in a space of distribution. So what I can always do is that I test with some test functions, f1, fn, then I obtain real valued processes, and then I take a nonlinear function of these processes, because this will allow me to characterize the law of the process. And then I call this phi of u, okay, and these are my cylinder function. And then when I write dx phi of u, essentially I imagine that I'm doing a small variation of u at the point x. And then the right way to think about it more properly is that, okay, I take my cylinder function, I differentiate in the kth variable. And of course, if I make a small variation of u, what I get is the value of my test function. Okay, this is my definition of this derivative, if you want. And somehow this is defining the dynamics at this point, okay? Because somehow all the operator I wrote now start to have a meaning. Especially I can write them explicitly, the linear part, but also of course the nonlinear part. But let's see, so the linear part with my derivatives, which were a bit formal, now everything is somehow well defined, okay? So this operator, it's well defined on cylinder function. So this is a Laplacian. So this will be my, if you want, my definition of the linear part. Okay, I'm still trying to find the proper formulation of my problem. And let me introduce at this point a similar operator, because we will need later on. So I told you this will play the role of my Laplacian, but in infinite dimension, unfortunately, you need more than one somehow metric to measure your things. And we will need like two kind of different Laplacians around. So this I will call the Oster-Uhlenbeck operator. So this is the linear part in my equation, somehow the part of my full generator. And I will need also this operator, which I call number operator, which essentially is another similar Laplacian, but you see as different coefficients. Okay, so these derivatives are not present anymore. So, and this has a meaning of a number operator in the Gaussian space. Okay, it's another kind of Laplacian of this form. Okay? And you can convince yourself that they commute, and actually on a Gaussian space you can diagonalize them at the same time. Okay? Via Gauss expansion. But let's say for me it's important that we keep in mind that there are two positive operators. Actually, maybe negative. So this is negative and this is positive. So this was a bit choice of convention, but I think then I got the sign wrong at some time. Okay, let not me discuss the sign because I got it wrong. But okay, somehow L0 is negative and it's positive. So maybe I got it wrong. And here, so let me write -n. The only thing it's important for me is that they are both needed and they commute, and you can diagonalize them at the same time. So it's not very difficult to deal with them together. The first part is the linear part of the equation. The second part we will need later on. Okay, so these are my operators. And so this is the linear part, so it's the easy part, okay? Well, I will not give a seminar if there were only L0. The problem is that there is a, why it's not, sorry. Yeah, I don't see it very well fit to screen. Okay. Yeah, so the problem, of course, is coming from the singular drift. And so let's look at it. So this was the drift. So I will rewrite it. And you see that the drift in this on cylinder function, again, which are just evaluation at a given point, is given in this very explicit way. Okay, so, and you see that there is, so this is the integral, for example, if you are in the torus, is the integral in the torus. Okay, you have to take, this is not anymore a cylinder function first, okay, because somehow here you have u squared, so in a given point you don't have u computed on a smooth function in a given point, and recall that somehow you expect that the trajectory, the state space of the system is the space of distribution. Okay, so this will not be very nice as a drift. Okay, so that's our problem. That's the main problem. Okay, so somehow this operator does not make sense. Okay, so we don't even have a definition of the problem because we don't have a good definition of G. Okay, so yeah, this is not a well-defined random variable. Okay, you can check by yourself. That is, you imagine that you compute U squared, then maybe you test on a smooth function. But then if you try to compute, even formally, you get the square of the delta function. And of course, you don't know what does it mean. Okay, this is plus infinity essentially everywhere. If you imagine to sit on the invariant measure. Okay, so that's the problem. Okay, so here I indicate L2 of mu, the L2 space of this measure, which is Gaussian and which is the white noise on the torus with mean 0. Okay, just a Gaussian measure with the covariance I wrote before. And then you can do a bit of functional analysis, which I will not describe because somehow it's just a detail of computation, but you see, you can try, you do a bit of this functional analysis and you discover that if you compute G phi, it's not a function because somehow you have this term which is not a random variable, so it's not something in L2, but if you multiply with the inverse of the Laplace, this Laplacian, the Austrian process, half of it, then you get an element in L2. Okay, so in this sense, it's a distribution on this L2 space in the sense that, okay, it's not an L2 function, but somehow you can regularize it and you know exactly how much you have to regularize it to put it back in L2. Okay, so it's, imagine that, imagine infinite dimension, okay, it's not a function, but if I take the antiderivative, then I get a function. Okay, this is exactly what it's written here. Okay, take half square root of the Laplacian. So it's somehow, if you want, is in the image of, if you want, is like half of the Laplacian of an L2 function. Okay? This is a very good measure of its regularity. And then this rejoin a line of research which was familiar to me. Somehow this is why I was interested in this problem, because it's a problem where you have a drift. So I call it a drift because it's a first order operator. Okay, you can check on a product of function, it satisfies the Leibniz rule. So it's a first order vector field, which is singular. Okay, and this rejoin a line of research of finite dimensional diffusion with a singular drift, and also this phenomenon of which is called regularization by noise. That is, the drift is singular, but because you have a noise term in the equation, this noise term helps you to deal with the drift, okay, which is singular, but the noise helps you. So in this problem, it's quite nice because the noise has two roles. The first role is that it produces the invariant measure, and so it produces your problems, because if there were no noise, you have a Laplacian, so the PDE has a very nice solution. It's the noise which is making the solution very rough and which make the drift not well defined. But the noise itself produces the enough randomness that somehow helps you to deal with this problem. Okay, you see from here, because somehow L0 is the generator of the linear part. So it's the noise and the Laplacian together, okay? The action of the noise of the Laplacian, so give you this generator. And then somehow it's this generator could help you to make sense of the drift. Okay, so that's our problem, okay? The drift does not exist. So you see, the problem is not that you are testing with a nice function, okay? So this function is infinity, but essentially think about in terms of infinite dimension, I could say the function is very nice, it's a cylinder function, but as soon as you apply the generator, as soon as you apply this vector field G, it's the vector field itself, which is not nice, and then produce a distribution, okay?
Massimiliano, this reminds a lot of Kipnis-Varadin's equations, no? That you have these
maybe
that you can, okay.
Yeah, no, but there is a lot of this, because somehow I think even Milton, I learned about like energy solution from Milton, and yeah, this is the technique of Kipnis-Varadin, how you do energy solution, how you estimate this equation. Now, my problem is that I don't know all this literature, and yeah, I can speak about this, and I will be interested to discuss, because somehow I don't know how to frame what we are doing in a classical context, if you want. Okay, so I can tell you what we do, and we try to read, like even in your book with Kipnis, or to try to find, like there will be a condition like this, how it's called, this, when you separate a condition on the generator on different levels. I don't remember now what is called this.
Gradient,
Sorry?
Gradient, you mean?
Yeah, this graded, yeah, this graded, and this does not fit our problem. And so we have, I mean, we tried a posteriori, we understood that there is some connection, and we tried to say, okay, does we fit into this context? And we don't fit. So I don't really understand where we are. That's okay. Also, but that's my ignorance, if you want, Claudio, because somehow it's not my field at the beginning, and also I'm very aware, you see, when I do functional analysis, I would like to understand what does it mean to me. That's why I'm really starting with very concrete things. So for me, the generator at this point is just an operator on cylinder function, okay? Because it's what is defined, what is my interesting equation, essentially, what I'm interested. Part of this problem, let me go back in my discussion. Part of this problem is that somehow, if you start from particle system, you have a reason to expect something. But if you start from SPD, the problem is, what does it mean, this SPD from the start? Okay, this was the problem in IRER also. If you look at SPD, the first problem you have is not existence, not uniqueness, is what does it mean, the equation you write. Okay, Kardarpati Zhang wrote the KPZ equation in 84, and you look at it and it does not make sense. Okay, so the first problem really you have to solve is, what does it mean, the equation? So here we are in a good shape somehow. Okay, we start to see what does it mean, the equation, because I told you, okay, I understand very well the linear part. I understand very well. Okay, I understand G has difficulties, but somehow I understand it very well in this sense. Okay, is G phi, I can give him a cylinder function, and they are not function anymore, but I can regularize and they are function. I'm not sure. Maybe in particle system, you don't see this problem in this very flagrant way, so it never happened to have a problem. But we have really this problem, that is G phi does not exist as a function. In particular, I cannot formulate the martingale. Let me go back. I cannot formulate the martingale problem very easily, because somehow I have to give, if I just to formulate the martingale problem, I have to prove to you that if I cannot think anything simpler than cylinder function. So let's put here a cylinder function, and then when I apply L, I don't have a reasonable function anymore. So I don't know what does it mean, this object, essentially. That would be one problem in the formulation. Okay, that is, okay, you identified an operator, but this operator brings me out of L2 in a space of distribution. So I cannot really formulate what is this integral here.
Yeah, this is exactly what happens in Kipnis-Waarden.
Yeah, okay, good. Then maybe I need to interested to see these things. But yeah, that was also, yeah, this is also the problem of math. This was solved by, this problem was solved by, essentially, the way we solve is like Milton and Patricia do energy solution. With maybe it's, I guess it's this Kipnis-Waarden idea. We call it Tito trick, but yeah, I'm interested to learn. So let me continue. For me, I was coming from this tradition, for this line of research of diffusion with singular drift, where we had similar problems. So I was interested to see, can we apply the same idea here? And there, the idea is the noise regularize and the drift become easier to deal with. Okay, so I'm trying to explain to you the story in the way I understand it. So they exist. So we talked about, so somehow now the problem is partly well understood. I defined somehow the operator. the generator, but still the martingale problem is mysterious because I told you G does not map in a space of function. Okay, so I cannot integrate this I cannot compute this G of phi on the process, and I cannot integrate it a priori if I don't know anything more. So what a reasonable person do is that, okay, I don't understand anything. Let me go back one step and let me regularize the drift so that I know where to put my feet. And the idea is that, okay, the first thing you do when you approach this problem is, okay, let's regularize the drift. I didn't write it down how you regularize because it's not very important. Just make sure it remains antisymmetric. That's an important property later on. But essentially, you regularize it in such a way that everything makes sense and that you can construct a Markov process and a stationary even Markov process, and you have a martingale problem to start with. Okay, now imagine we have this approximate generator where L0 I don't touch because I don't need to touch L0, but G I have to approximate G. For example, if you want to see, instead of taking the square, you just regularize U and then you take the square. Okay, that would work. But if you want just a finite dimensional approximation, you do Galerkin. So you approximate everything, and the state space you take, you make the nonlinearity act on finitely many modes, modes, variables. And so you have a martingale problem that's standard. Okay, essentially it's a finite dimensional Markov process with nice properties. And now the idea is, okay, then I want to study this. And the idea here, which I learned from Milton, essentially, was this energy solution method, which they used in the particle system. And we wrote a paper with Milton to apply to PDE. Okay, this is the first time I learned about this. And the idea in that method somehow is that, then there are various ways to do it. Okay, the way I found nicer is the way it's explained in a paper of Olla and somebody else, which maybe I don't remember right now, where they look at the forward and backward, and so they look at the process forward, and then you look at the process backward, and when you add up the two things together, somehow you cancel the antisymmetric part and you can estimate. That's how I learned about that. And since at some point you use Ito formula to do that, and I come from another line of research when we call it Ito trick, I start to call it Ito trick. That is, you do a computation on the martingale problem, and you realize that now when you have additive functionals, I agree with you, Claudio. Yeah, I understand what you say about like this the estimation of the additive functional with the like H minus one norm.
Yes.
This is Kipnis-Varadan. Yeah. That's. I think somehow when I found it, I think in the literature, maybe Kipnis-Varadan is in L2, no?
L2, yes.
And if you want these estimates, which are nice to have in SPDs, because somehow you have this Gaussian and you have all this integrability to take care about, then the method I know is this method of Olla, which look forward and backward. So you sum the two martingales and then you get better results. But okay, the substance, these are methods. So somehow I think what is conceptually important to me is that you have an estimate like this at the end of the day on the approximations. This is the idea I get from Goncalves and Jara of the energy method. That is, you have this on the approximation, and this estimate, it's very nice. Tells you that you can estimate additive functional of cylinder function, but then you can extend by continuity to other functions in terms of you see a weak norm of the function. Okay, you don't estimate a priori. The easy estimate here is that you take the absolute value inside, and then you have the invariant measure, and you have the L2 norm of phi with respect to the invariant measure. But here you have a weaker norm. Okay, you have the L minus 1/2 norm of phi. And okay, here this weight don't take care. If P is equal to, there is no weight. Okay, but this is like a constant to the power of this number operator, and this is needed If you want the LP norm, then you have to use hypercontractivity to go back to the Hilbert space setting, and then you have to introduce this weight. Okay, so somehow here the idea is that if you want higher integrability, P bigger than 2, then somehow your cylinder function is to be such that it integrates a weight which is exponential in this number operator. Okay, so somehow it has to decay in the eigenspaces of n, it has to decay fast enough. But okay, that's a technical point, okay, if you want P large. But that's the key information you want on your approximation or on the microscopic system. And this information you cannot recover in the limit. So the idea I got from Goncalves and Jara, that is how I understand their method, is I keep this information as a definition in the martingale, when I speak about the martingale problem in the limit. So you have this for any Galerkin approximation, it's uniform in M, so it passes to the limit. Okay, and then, okay, so, and this in particular at this level give you compactness, so allows you to take limit here. And it gives you even more, okay? It tells you somehow that you can define now this object in the limit, because you see that you don't need to require that this function now it's in L2. It's enough that it's in a space of distribution. This is what we have, okay? Our drift is in a space of distribution. So using this tool, Goncalves and Jara were able somehow to deal with drift which were distribution. And why I spoke about regularization by noise, somehow here the idea is that this functional could be so now in this formula, this functional can be a distribution, because you just then regularize and it will be in L2, so no problem. And what they say, so how I interpret this formula is that, okay, this object is irregular, but somehow the process is fluctuating in time, and the time integral regularize. Okay, you just see an average, you don't see exactly the function. Okay, so here the game is that you don't want to take the absolute value inside, because otherwise you're lost. Okay, you don't get an estimate like this. But as soon as you look at the integral, the process decorrelates quite fast in time, and then you get a better behavior. Okay, this is how, and this happens also in finite dimensional in other problems, and this is part of the topic of regularization by noise in that line of research. Okay, so this gives you compactness, but the point now is that you want to keep this information because it's precious to you, so you want to use it, and you define a new notion. So this is somehow what we called it, but essentially it's energy solution. But since we wanted to have, so in the papers we call it a cylinder martingale problem. And now you can formulate your problem, okay? So somehow now we have somehow the elements to formulate a problem. That is, sorry, let me go back, okay? Here we had, of course, a sequence of processes, and I told you this Ito trick give you compactness, or Kipnis-Varadhan estimate give you compactness, and then you have any limiting point would be solution of something, okay? You can pass to the limit n at every level here. And so the limit point, so you have to encode what is the right notion of solution. And so it will have 3 properties, which I write it now. So the first one, so you have to encode many things. So this is the kind of information you want to track from the Galerkin, from the approximation to the limit, in order that then you can do other things on this limit, okay? So, but again, okay, there are all the properties that you have very naturally on the approximation you think you would like to make. Okay, so we need all 3. So the first one is that somehow the process is what we call incompressible, for reason linked to, again, to finite dimensional situation. And the idea is that you want that every time you can compare the law of the process with the invariant measure, okay, in L2 at least, okay? So this is true for the Galerkin approximation, because especially if you are stationary, you have really equality, okay? You have equality here. And this is compressibility means that somehow your dynamics does not concentrate the law of the process in region where this does not agree with the Gaussian measure. Okay, so at any given time you can compute this kind of functional in the L2 of the invariant measure. That's very helpful for us. And these are all limitations of the method, if you want. Okay, if I don't have any of these properties, then I don't know what to do. This, for example, implies that I cannot start far away from stationarity. Okay, so somehow you have to guarantee that your process is not very far from stationary. Otherwise, I am not able to do computations. Then the limit also satisfies the Ito trick. What does it mean? Well, for any limit accumulation point, you can pass to the limit in this inequality. And then you get the same inequality. Okay, so this is a property you cannot regain back. Okay, so you have to take it with you. Otherwise, if you lose it, you are lost essentially, or I'm lost. And there are other ways to formulate it. You could say that the process is reversible, that is forward and backward. I've prescribed dynamics, but for this talk, it's okay to say that it satisfies the trick. Okay, and then of course you have the description of the dynamics, because at this point, so the point of the first two condition is that with incompressibility and the Ito trick, you are able to define L of phi. You remember, with incompressibility, essentially you can define L of phi of u, because you know that the law of US is comparable to the L2 space of the Gaussian measure. So essentially you can do L2 computation. So I can compute this, and this will be a distribution in the Gaussian space, because I told you there is G. And then again, that would be a problem, but the Ito trick saves you, because then the Ito trick says to you, okay, this is a distribution, but if you integrate in time, it becomes an L2 function. So it becomes a function. Okay, so this is an L2 random variable now. So this is well defined. Of course, you have to prove these things, but somehow this is the broad picture. And then you have defined this. So now you give me a test function. I can compute these two terms. I can compute this because I can use these two conditions. And then I can check if your process, the process is a martingale, solution of the martingale problem or not, because the process I obtain has to be a martingale. And this is the definition of the martingale problem. Okay, so all this work up to now, we made it to be able to have a well-defined problem. Okay, so this is the starting point. This is the problem I want to solve. I want to ask myself, okay, I prove to you essentially right now the existence of solution to this martingale problem, okay, because you take Galerkin approximation, you pass to the limit. Any limiting point is not difficult to see that they satisfy 1, 2, 3. Okay, so this is a point where we have a good notion of solution. It's meaningful because I can prove existence, and actually it's natural because essentially natural object converge to this notion of solution. And so the only question remains at this point of the talk is it unique? Okay, so did I specify the notion of solution well enough that I can guarantee uniqueness? Okay, so that's somehow a point where the seminar go into different directions somehow, because uniqueness was the main open point for some time. With Nicholas, we found a way to deal with uniqueness for KPZ equation, for the martingale problem of the KPZ equation. But these were using a lot the property of KPZ, in particular that you can approximate the Hopf-Kohl transformation. But that's not what I want to talk about today, because later on we found this other method which seems nicer. And this other method deals with proving directly that this martingale problem has a unique solution. And usually, as far as I understood, the normal technique to prove uniqueness of a martingale problem is that you have to study the duality with a backward equation, okay, in the sense that, okay, here I didn't wrote the statement full statement. What is the idea? I think the idea is more interesting to me. So you want to prove uniqueness in law of the martingale problem. That is, okay, you give me a process which has these three properties. Can I prove to you that it has a unique law? That there is only one process which has, okay, that the law, it's unique. Then the idea somehow is that you should be able to plug in nice time-dependent test function in such a way that you can do a martingale argument of this form. Okay, imagine that, for example, I want to determine the 2-point marginal of the process. So I want to determine the law. So you start, the idea is that, okay, you want to determine the 1-point marginal, the 2-point marginal, and so on. So finite time marginals, and then this determine the law uniquely. Okay? To process which has all the finite time marginal, finite dimensional marginal is to be equal in this setting. And then the idea, for example, for the 2-point marginal, what is? Well, you have a function phi and psi, and the idea is that you plug in a psi. So psi you choose, okay, but then you somehow you see at the final the final value of a Cauchy problem. And so, okay, if you just use the Ito formula, okay, from time t to time s, then you can write phi of ut as this expression. Okay, that's Ito formula. That's the martingale problem. So formulation and the fact that the martingale part disappeared because this is in the past. And then if you can make this 0, then you, sorry, here I'm wrong. Okay, you have s, of course. Then if you can make this 0, then you can make this 0. So I don't like a big parenthesis. Then, of course, what you remind is that. So, provided you know that the 1-time marginal it's unique, then you know also that the 2-time marginal it's unique. Okay. And so in order, that's the idea, okay? Once you have done, and this allow you to reduce any endpoint marginal to a 1-time, and then from 1 to 0 is the same argument, essentially, okay? Provided provided the law of the initial condition is known, then the law of the process is determined, okay? That's the idea of this duality. And what you need to be able to find functions. Essentially, you look at the argument, you think a moment, and essentially you need functions which satisfy classically the Cauchy problem for the generator. Okay, that's the way I like to tell this. Okay, that's the concrete what you need in this argument. Okay, so you need, because you need really to be able to compute things, and you need classical solution in order to be able to, because you see, you need function which depend on time. So here you really need to take the time derivative, and so here you cannot use. I don't know how to use in this argument the Ito trick. Okay, so here you really, when you apply a test function, you have to be sure that the generator applied to the test function and the time derivative applied to the test function are in L2. Otherwise, here you cannot then continue the argument, as far as I understand. And so that seems a requirement for uniqueness in this setting, and it's the natural requirement. So provided I can find enough classical solution. So the idea is that you need enough classical solution of the Cauchy of this Cauchy problem. Okay, well, you need enough because you need to plug in a lot of phi, and this is the initial condition. The Cauchy problem is taken backward in time, of course, and so you need to plug in enough function to determine this marginal. Okay, so you need enough solution of this Cauchy problem, which are classical in the sense that these derivatives, this right-hand side is in L2, and the function is differentiable in L2, at least. we can work in L2 because somehow we have this incompressibility condition. Okay, so I know that at any given time the law is comparable to this thing. I can compute things in the L2 space of the process. Okay, so that's the need. Okay, so that's the problem. So can I solve the Cauchy problem for enough initial data or not? And you can restate in a different way. So what is the domain of this operator? Okay, but I think at this level it's not even a question of domain. Of course, if you know the domain, you can solve the equation. Okay, because of course you can construct. Okay, that's all the problem. Okay, the problem is how you want to solve this equation. Then you can start looking at functional analysis, and okay, you maybe want to prove that this is a generator of a you have various choices. Okay, either it's a self-adjoint operator or a generator of a semigroup, and then maybe you can solve this problem in these two situations, for example. Okay, so and part of the problem, so here the problem is you see, you want, okay, here is the way we solve the problem. Then I will tell you what. So somehow our point of view on this problem was that we were looking to this problem as a PDE. Okay, this is a PDE for us, a parabolic equation. You have a Laplacian, you have a nonlinearity here, or in some sense a difficult term, not very explicit, and the Laplacian, you know everything about it. And the difficulty is that you already know that this object is a distribution. Okay, so if you want that the sum of these two is in L2, because somehow you require like these conditions, somehow you require the condition that, yeah, the time derivative has to be in L2. Okay, so you need that the right hand side has to be in L2. So for this to be in L2, what should happen is that since this is a distribution, you already know that you don't have much choice. Okay, the function phi cannot be too smooth, because if this is in L2, then this function in L2 can never compensate a distribution. So the sum has to be a distribution. Okay, so this object has to be regular enough to cancel this term. Okay, that's a bit the idea we had. And how we implemented this idea, we had some idea, since we were looking at SPD, singular SPD, we had this idea of controlled function, because somehow what you need, as I told you already, it's that you want to compensate. Okay, so the Laplacian has to compensate for the regularity of G. Of course, if you know the domain already, that will happen automatically on the domain. Okay, the problem is how you construct a domain for the operator, and how you have enough information that later on we will need to do some other operation like approximation of functions in the domain. So you cannot just proceed abstractly. Okay, you need the information on a concrete way on the domain, and essentially this tells you that the domain cannot be made of, there are no smooth function in the domain. Okay. That's the first information you have, because if the function is smooth, then this would never be essentially approximately equal to that, in the sense that capture the regularity or the singularity of that term. And then, okay, here is the way we proceeded. It's not the unique way, but somehow the idea now is okay, let's separate G into parts. Okay, so this is what we did. There is a reason I will tell you later, but somehow you start to estimate what is G of phi for nice phi, and then you realize that somehow you have some trade-off and you cannot win always. So somehow there is a part. You want to separate the space. Okay, so somehow here you are looking, you see here you look in a part of the state space where L0 is bigger than some power of the number operator, and you put a parameter there, and this you give a name to this operator. Okay, and then you take the what remains. Okay, And somehow this part of the operator encodes the difficulties. So somehow this is the origin of the singularity when you apply in the image of G. Okay, so this part it's easier to deal with. So you separate the singularity, but in this part you know that somehow you have a relation between N and L, and this helps you, because the problem here is that you have two notions of regularity. There is the scale given by L0 and the scale given by N, and G somehow wants the two, okay, needs some powers of L and some powers of N. While in your original problem, so let me go back. So somehow in this, the PDE only knows about L, does not know about N, okay? So somehow if you think as about parabolic equation, it regularizes in the scale of L0, but it does not regularize in the scale of N. While G wants both, and so you have to have a trade-off at some point, and you decide to do this kind of trade-off. And okay, so now, yeah, I see that it was already 1 hour I speak, so maybe I realize that I have still many things to say. Maybe I try to speak 10 minutes and then we will see, Claudio, you will tell me.
Perfect. Yes, okay. Sure.
I will try to compress the message in 10 minutes. Then there are some computation. If you want, we can look at them. Yeah, sorry, let me turn on the light moments. Okay, yeah, sorry. Okay, so here the idea. So you separate the difficult part into parts, G superior and G inferior, let's say. And because somehow this leaves you this freedom here, you choose the chopping. So maybe you can opt to optimize it later. That was our idea. And now the problem I want to solve now, it's really, I need to find a space of function which has this property, okay, where the two things compensate, because somehow I want to construct a space of nice function for the generator, okay? I want to construct function which, if I apply to the generator, they give me function in L2. And then I hope that this is somehow a domain for or allows me to get a domain for the operator. And how we do? Well, now you solve an auxiliary problem, okay? So the idea is that you give me a function which I call f sharp, and I solve this problem, okay? This is a fixed point problem. So I find a function phi, which is a solution of this equation, okay? And you see, I apply the difficult part of G, and then I regularize. And essentially, okay, this is an equation. It's an implicit equation for phi, but essentially you can solve with a fixed point, because with my choice of chopping, I can guarantee that this object is small. Okay, so I can choose L large enough and estimate 2 or 3 pages and show that, or maybe even less, and show that this object somehow it's small, and I can solve this equation by a fixed point, let's say in L2. Okay. And this gives me a map. So for any function phi sharp that you give me, I can construct a function phi, which looks like this, okay? And then you see, okay, what happens if I apply the generator to this kind of functions? Well, you apply the generator to this function, okay? So L phi, and then you apply L here. And of course, this disappears, so you get G superior phi 0. Okay, and you check that, okay, you do a computation and you check that you get this. That's not difficult, okay, from this. So L0 applied here give you the G superior, and L0 applied here give you this term, and then you have G phi, but you have already minus G superior, so you remain only with G inferior, okay? So on this space of functions, on the image of this operator K, which you constructed by fixed point, L has a nice form, okay? That's the message, that is L0 phi you can choose, because phi you can choose as regular as you want, okay? So L0 phi is in L2, and then you prove that for the functions in the image of K, G of phi, so G applied to K, applied to something, it's a nice function, okay? So somehow this operator K, which we introduced, do what we hope him to do, that is implement an approximate version of this equality. Okay, it does not solve the problem because I don't want. This is a preliminary step. Okay, if I'm able somehow to find function which like solve the resolvent equation or the Cauchy problem, that's my main goal. Okay, how I solve the Cauchy problem or how I can solve the resolvent equation. It's the same thing. Or how you prove the resolvent. Some relation for the resolvent. But somehow this is a preliminary step, easy, because somehow you can choose a parameter, then this is you just do a fixed point, there is no difficulty, you control the estimates very well, and then you discover that what remains, there is still some work to do, but it's easier. Okay, so you somehow you encoded the difficult part. In particular, you can hope that the image of K give you a nice domain for L, okay? Because L on the image of K goes in L2, so certainly this image is in the domain. Maybe the natural domain it's bigger, okay? But certainly it's a good starting point, okay? So this is the main idea contained in our initial paper. I'm not sure if one can express all this. Yeah, I will maybe comment about it. Okay, so this was so one you introduce this give you a domain. Okay, these are a lot of maybe I had a lot of computation here, but there is no point to go through all of them. Maybe just want to show you in the paper there are a lot of this computation. They look scary, and every time I read them, I have to go back what they mean. But somehow, this is the kind of things you have to look at. Okay, so for example, you have to estimate the operator G superior, and you have to understand somehow how it behaves in weighted space with respect to L0 and N. So let me not go through. Maybe I just to mention that it's not very important at this point. Maybe we can have a more abstract discussion. I think I wrote it down because they were coming from another talk, but I never managed to talk in detail about the estimate. It's not really important. It's just these are technical points because you have to deal with two spaces with two weights because the operator G needs two weights. That's okay. But the point is that our decomposition is made in such a way that somehow we could define a domain for the operator. Okay, so somehow the point of view we took in the paper is that we define a domain by taking the image of K for a certain class of functions, and you have to guarantee that this function are in some weighted spaces because you need integrability at some point. And of course, this is a nice domain in the sense that the image of the operator is in L2 and the domain it's dense in an appropriate weighted space. Okay, and all these quantitative details are needed later on. Okay, somehow I don't know how to get rid of all these details, and I especially I don't know how to proceed more abstractly. Okay, because it seems that somehow many of these quantitative details, if not all, are needed later on. So let me maybe, then, okay, this is, I gave you broad lines how to obtain a domain, and you define, now it's a densely defined operator. Let me just copy this part. So it's a densely defined operator with this domain, and but let me note that you are not in a standard context in the sense that, for example, if you put a constant in front of the drift and then you change this constant, then the domain are disjoint. Okay, so you define a family of operator where you put a constant in front of the perturbation if you want. Then you get a series of domains which are disjoint. Okay, so as soon as you change this constant, two different operator and lambda they don't agree anymore what are the nice functions, okay? So that's not what you see, for example, if you do Kato-kind perturbation theory, where you can dominate G with L0, then you expect that somehow G is dominated by L0 point. The domain is determined by L0, not by G. But here it's somehow really the exact combination. So the function in the domain are such that they really combine exactly in some ways, and as soon as you don't put the right number here, they don't combine anymore. And so another operator maps them in a very bad space. But okay, in its own domain, let's say lambda, when I don't write lambda is 1, okay? When in its own domain, the operator is dissipative, okay? It's nice because somehow G is antisymmetric, okay? So when you test with phi, you only see L0, and then L0 is nice, so the operator is dissipative, and its adjoint is the operator with lambda equal -1. Okay, so the domain of the adjoint is different from the domain of N. And they are incomparable. Okay, so this is just to say, this is our operator. Okay, so now the problem remains how we solve so we have defined an operator, but is the right one. So because remember at the beginning, I just wanted to solve the Cauchy problem. Okay, I don't. That was my point of view. So how we solve the Cauchy problem? So we took in our first paper, we took a very hands-on approach. That is, we look at the Cauchy problem as a PDE. So this was the backward Kolmogorov equation. So you look at it as a PDE. You start from somewhere, and this somewhere is that you go back to Galerkin approximation, and then from them you have a Markov process. So you can construct solution of the backward equation via Markov semigroup, okay? Because you have a Markov process. And then now you have a starting point. You have a solution to some equation, and you need to pass to the limit. And then you start to do, I don't know, I'm more used to PDE kind of thing. So I start to do estimates for the PDE. So I test with so what you do here, you just test with the function, then you integrate by parts, and you get an estimate. Okay, you have the dissipative part, which helps you because it's positive. And you have the drift, which is the enemy to fight in this estimate, because everything on the right, it's good, and everything on the left, it's bad. And then you hope that you can estimate the left-hand side with the right-hand side. And you have to put, if there were no weight, so if there is this weight here, then G is antisymmetric, so this disappears. Okay, so this would be a good estimate. Of course, it's just the index that the operator is dissipative, and then maybe you can pass to the limit. But we needed more information. So it's not enough to pass to the limit into the equation. You need some more information later on. And so you need to understand how the weighted norms of the Cauchy problem behave in the limit. Okay, so you put the weight, and then you compute, and then this term does not disappear anymore. This is related to this estimate we were talking before with Claudio. That is, you have to understand exactly what the operator G is doing with different value of N. So how it's moving things around for different eigenspace of for in the end. And yeah, and then, okay, here you do estimates, and you have hope that things are working out, because somehow G is losing regularity, but somehow you have some regularity here. And yeah, let me see if I want to. Yeah, let me just keep the computation. So somehow at the end of the day, you can do a computation here, and you obtain an estimate of this form. Okay, so all the problem is how to estimate the right-hand side. And somehow G loses in the powers of N, but so you can, using the antisymmetry, you go back to an estimate which you can handle, which looks like this. Okay, so you have the good terms on the right-hand side. You have used a bit of this regularity to beat the bad term. and you remain with a term like this, which is good for you because it's exactly that, and you can use grown one. Okay, so this term is positive, you can neglect, and this term you control with grown one, and then you are happy. Okay, and that's
I see that people are starting to leave from the audience.
Okay, yeah.
No,
so
no, maybe take some time to conclude, but
yeah, hurry up. Yeah, okay, let me, because I finished somehow, that's the idea. Okay, so somehow this is the kind of idea you use, and then you pass to the limit. And yeah, so in the, okay, I have just my last slide. Yeah, sorry, thanks for reminding me. So let me just give the moral of the backward equation. So so in our original paper, what we managed to prove, somehow we had solution of the, so we have this domain, okay, and then we solved the Cauchy problem, and by looking at the regularity of the Cauchy problem, somehow you prove that you find solutions which are the right regularity you want. Okay, they are continuous with value in the domain, and C1 with value in L2. This is like L2. Okay. Still, this was not somehow didn't fit in a standard setting, because we could not start this solution from any point of the domain, for example. Okay, we had to start from a smaller space. So you need to take initial condition in a small space, and then you have solution evolving in the domain, which we defined before. So that was fine. But somehow the initial condition, so you could not, you cannot restart. You cannot start from any point in the domain. And then you prove, okay, but this is enough to prove that the operator has a unique closing extension, but somehow maybe an index that the domain was not right. But this was enough to have uniqueness, okay? Because the only thing you care somehow is be able to have a solution of the Cauchy problem for enough initial conditions. Recently, I told you this thesis of Grafner, a master thesis, where he find a nicer argument by using more carefully the antisymmetry, and he really can define can solve the Cauchy problem for any point in its domain. Okay, its domain is defined a bit differently. And I finished now. So let me just maybe, I have a out. No, let me maybe just mention the extension, because somehow the summary I gave. So just to tell you that all this works for other equations. In the paper, and in other paper, there are multi-components equation dealt like Burgers, or fractional Burgers, like where you use less than a full Laplacian. And I think with the strategy, in the paper of Perkowski, we have uniqueness now for any theta bigger than 3,4. But if I understand the result of Grafner, he can do also the critical point. Okay, that would be very interesting. And in the paper with Tura, we look at other equations. Okay, so I stop here. Thanks for listening. Yeah.
Well, thank you very much. So, and so it was a very nice talk. Thanks.
Yeah.
So we are open for questions.
Graded sector condition. Yeah, that was.
Yeah. So Milton.
Hi, Massimiliano.
Ciao, Milton.
So, okay, no, it's a simple question. So, some time ago, when I spoke with Nicolas about this result, that was a few years ago, yeah, already. It's so the fact that the invariant measure was invariant was important.
Yeah.
And but let's say that I want to be satisfied with something weaker. I don't want just I don't want to prove uniqueness of the martingale problem. I just want to prove existence of the backwards Kolmogorov equation, of solutions of the.
Yeah, but you see so the point is what you. So the Kolmogorov equation is a PDE problem on the state space. Okay, so there you have to choose a measure. Yeah. So there, I don't know what to do else than, especially in the paper, we really use a Gaussian like calculus. You have to be able to work maybe more abstract. So somehow in the paper and in the, I think even in the more recent paper, we need to do estimates. Yeah. And so you really need to do computation on the Gaussian. Maybe one can do something more abstract. But the point is, I think the constraint about the measure is the process. No, if the process do not agree that the support of the Gaussian measure is the important part of the state space, then somehow the Cauchy you don't know to solve the Cauchy problem from this point of view of the Hilbert space. There is all the school of Da Prato, which they look at the Cauchy problem not in the Hilbert space, but in a space of continuous function. So it's a problem of PD in infinite dimensions. So what is the functional setting which you can handle? So since things are distribution, I don't personally, I don't know to do anything else. I would need a concrete example and a motivation to think to a more concrete situation. You see, I cannot just imagine, okay, you don't want to take the invariant measure, what you want to take. There is nothing else around.
Yeah. No, I mean, what I was thinking is that maybe there is this process for which you say, okay, the Gaussian is not invariant, but I have faith that the invariant measure maybe is absolutely continuous with respect to it. And then it makes sense to look at the problem in that.
Yeah, this I understand. So we are trying to read your papers and try to use them. Yeah, one strategy could be, for example, no, you could imagine, this is what we are trying to do, like take a measure which is Gaussian at every time, but maybe the covariance depend on the time, for example, okay, just to understand. This is in the spirit really of your work with Menezes, no? You try to find, maybe your process does not have an invariant measure, or you don't know the invariant measure, you try to approximate, and then in the functional, to be able to study the things, you want to have a Gaussian measure, because then I'm happy, I know everything. So I try to approximate with a Gaussian measure, which could depend on time. So maybe here you could allow something which depend on time, with a covariance which depend on time. So somehow all these Gaussian measures are not absolutely continuous, but you don't care. I think this could be doable, but one should need a motivation to do that. I don't have right now a really good example, but that could be an example where all your measures, they are not absolutely continuous with respect to one another, because maybe you change the covariance, but somehow at any time it's and actually it's an interesting problem how to deal with the that would be a Cauchy problem, like in a somehow where the state space depend on time, because it will be the L2 space of the measure at a given time. That's I don't know how to do actually, but that's interesting. Yeah, we were trying to think in terms of your work, but it's still not clear to us how to use it. With you see, particle systems are quite nice, because I mean variable it's plus or minus one. Gaussian process are not plus or minus one, and when you start to have polynomial of Gaussian, so the problem we have right now is that when you start to have polynomial of Gaussians, you see you have to do the exponential estimates, no, because you control only the entropy. Then polynomial of Gaussian you cannot exponentiate.
Yeah.
Okay, that's the problem. To import your technology in this SPD context is not so obvious. We are just blocked at the beginning because we cannot use the same argument. And since you don't only have the entropy, I don't see what to do. So it's complicated.
So any other question? So let me ask, if you consider all the models, so the ones you mentioned at the end, so where is the crux of the proof? I mean, where you really need to new argument in this, because what you presented looks a complete strategy in order to derive
In all this model, more or less is the same. In the model, I understand. I don't, of course, this weak universality stuff, they really work with microscopic models, okay? But if I look at the SPD, so the other model, which I understand, the strategy is the same. It's just that you have to redo the estimates for the drift, but maybe the exponents are different, but the global strategy is the same. There is a point which is, you see, we don't fit in your, so somehow we cannot fit in the setting of your, this graded setter condition, because I think here you need to have this loss of n to the power beta, and beta has to be less than 1, something like this, if I remember. But we have really a loss of power 1 somehow. So I'm not sure. So in this estimate, we cannot fit it in the setting of your theorem. That's what I mean.
Okay.
I'm not sure. There is a point where you have a grow in n, and then you have this setter condition, no? And the grow is less than 1 power of n, and we have really only exactly power 1 of n. But it still works relatively easily. Now I skipped the detail, but essentially I really looked at this as a PDE, and you do some estimate. You have to use, the only trick we use is that this weight. So somehow what we do is that we separate the space in a region where n is the dyadic region for n, okay? And you have to take this region with you cannot take a indicator function to separate the region. So this weight cannot be the indicator function that n is to the dyadic, okay? It has to be smooth. And if it's not smooth, we cannot do the estimate. So, and this you see in PD theory, you have the same problem. So you use usually like smooth partition of unity. If you use a hard partition of unity, it does not work. So maybe the same thing works in your book. I'm not sure if you use you see my problem there. So if we use a smooth partition of unity, somehow things cancel, and we are able to gain the power of n that we lost from an estimate. Otherwise, we cannot. So, as I told you, I don't understand. Your comment, I understand like this. No, what is the general theory behind all this? And I don't know. I don't know because I don't understand very well the general theory. This thesis of Grafner, so he constructs the domain more directly, and essentially is able to use Lumer-Phillips theorem to construct the operator, okay? Because he find a domain, and essentially he find the right answer for the domain, and then the operator is maximally dissipative, whatever. He can use Lumer-Phillips theorem. Essentially, he solved directly the resolvent equation. You know that the image of the resolvent is the full L2 space, and then it's done, essentially. But still, you have to do some. So that's not the full story, because somehow the original martingale problem, there are still, you see, I don't, at the end of the day, there will be a Markov process, okay? But I cannot go around the martingale problem. So everything comes out from the martingale problem. It would be nice if somebody understand it, because we don't understand, and we rely, in our mind, there is no useful Markovian point of view. This is what I think. It's difficult for me to have a Markovian point of view. So we always use the martingale problem, and you see the part of the point is that the martingale problem is formulated, for cylindrical functions somehow. While the functions in the domain, there are no cylindrical function in the domain, okay? So at some point you will have to approximate functions in the domain with cylindrical functions. So you need to know somehow the domain quite well to be able to do that. Otherwise, even in the thesis of Grafner, which is simplifying some other argument, then it has to do some explicit computation in this approximation step. And so I don't know what is the general theory behind, if you want. Okay, that's all.
Any other question?
at the end there is a Markov process. Okay, I didn't say, but essentially when you have uniqueness of them, but again, okay, the Markov process you can start only from L2, because everything is linked to this fact that initial conditions are in L2. So you cannot say I can start from any. I don't know what is the state space somehow. Yeah, it's some. I'm a bit vague about that. There is a semigroup in L2, and then you can construct a Markov process if you start from initial conditions which are in the absolutely continuous with respect to the Gaussian measure. But I cannot really have like a Markov process which proceeds from point to point. No, I can construct stationary processes which are Markov processes, but I'm not, apart from that, I didn't thought a lot exactly how does it fit in the general theory of Markov processes. So.
Good.
Okay.
Well, any other question? Well, if not, thank you a lot, Massimiliano. It was very interesting talk.
Thank you.
Very nice.
And for the patience for 1 hour.
No, it was really nice. Thank you very much.
Okay,
and
thank you.
Take care.
Bye. To the next time we are able to meet in person.
Yeah, let's hope.
Bye. Ciao, Milton. Ciao, Pablo. Hi,
Ciao,
everybody.
ciao.
Thanks a lot. Ciao, Tertulia.